Welcome to part 3 of this lecture on bevel gears and worm gears in the course Advanced Machine Elements at Luleå University of Technology. This part we will be discussing forces that you can find in bevel gears. And the resulting force, Fn, can be divided into components as shown here, where we have Fr, which is a radial force, Fp, which is the peripheral force, and Fa, which is the axial force. Now, according to the figures shown right here, you see that the radial force is related to the normal force, or Fn, with the alpha n angle. Then we have the peripheral force is related using the alpha n and beta angles, and the same thing for the axial force, but in this case we have sinus for the beta angle. Fp, the peripheral force, which is the force that is actually transmitting the torque or generated by the torque, is calculated using the applied torque to the system. So we have Fp and we have the torque that we apply to the gear, and R times sine for the pitch angle according to this figure that you see right here. Based on this, we can then calculate the axial force as the peripheral force times tan beta, and then we can go on to the radial force, which is equal to the peripheral force and this expression using the alpha n angle and the beta angle. Now the resulting force, that will act somewhere between the big end, that is the outer end of the gear, and the small end, which is the one towards the center. It is therefore, based on this, assumed to act at the center of the gear tooth. The radius at the center, which is called Rm, m for middle, or you can relate to the center, is calculated as Rm equals Re minus b over 2. And you can go back and look at the figure showing the geometry of the bevel gears to find how this expression is derived. This then gives you the peripheral force at the center as the torque divided by Re minus b over 2 times sinus for the pitch angle. And with a load factor and a dynamic load factor that we can get from diagrams, we finally get force that we can use to calculate contact stresses, the expression shown at the very bottom here. Now the stresses in a bevel gear, they are calculated using what is known as an apparent cylindrical helical gear. This way of doing it is called the Treadgold's approximation, and the figure is trying to show this in a more clear way. You have a real bevel gear, the green one right here, and you have another real bevel gear right here, the blue one. Now to calculate the stresses, we transfer this into a apparent cylindrical helical gear system. So here is one apparent cylindrical helical gear, and the other apparent gear is right here. So we still have the contacting gear teeth right here, but we transfer this to a apparent cylindrical gear. What we have to do now to make this work, the apparent helical gear will get different number of teeth. Since we keep the module and the pitch constant, the number of teeth will change. So we calculate ZV, which is the apparent number of teeth, based on these equations, where we set 2 pi Rm, which is the radius to the center of the gear, sine for the pitch angle over the number of teeth, relate this to 2 pi Rv over Zv. And this can then be simplified down to Zv equals to the number of teeth divided by cosine for the pitch angle. The gear ratio then for the apparent helical gear will not be exactly the same, since we're using the apparent number of teeth also. So we have ZV1 or ZV2. This is equal to this if we want to relate it to the real number of teeth. And then we transform the number of teeth to an apparent spur gear, ZVN1 and ZVN2, according to this relationship or this equation. Now, once we've done that, we can then move on to calculate the contact stress, which is approximately given by this expression. And in this case, this force is the one that we derived earlier, based on the derived from the torque that we apply, these load factors, the radius to the radius and minus the width over 2, sine of the pitch angle, and then we have dm1 here, which is given by this expression. There's also another way of calculating the contact stress based on the same for this FPM, which we have derived earlier, and this is then divided by the face width, pi, times the module, times y, which is a tooth form factor. And this is something that can also be taken from literature or from diagrams. And re is the cone length, again minus the face width here over the cone length. So this is an alternative way of getting the contact stresses. So to summarize the bevel gears, they are quiet, they are efficient when it comes to the efficiency of the gear system, and you typically employ such gears when you have non-parallel shafts, meaning that you have, for instance, 90 degrees between the driving and the driven shaft. Then you would introduce a bevel gear to get that torque out to the gear, to the shaft that you need. So that ends the part on bevel gears in this lecture. Thank you for your attention, and hope you will enjoy the fourth part on worm gears.